Hello everyone. Today we're going to talk about Hamiltonian circuits. As you may remember, the TSP problem or traveling salesperson problem is given a graph, let's say a list of cities that are connected to each other. We're going to find a path, or we're going to find the shortest possible path, starting from one city or one node and like visiting every other node exactly once and going back to the start city or start node. Okay. So, and we use the dynamic programming to solve that problem for a small amount of number of cities. The Hamiltonian circuits is about finding if there exists such a path that starting with one node, if you can visit all nodes exactly once and going back to the city that you started. So here we have a graph with 4 nodes. So as n is equal to 4, or the number of nodes is equal to 4, and let's say that we are going to start from node A, and we are going to visit all other nodes exactly once and go back to node A. So one solution, and just the only solution in this graph, is starting from A, going to B, B to C, C to D, and finally from D we are going to N. So that's a Hamiltonian circuit, and we visited every node exactly once, and the start and destination both are A and they are same nodes. So using backtracking, we can solve this problem, or see that if we can find such a path. So similar to what we had for the n-queens problem and also the graph coloring problems, that we are creating some sort of a state space trees. So we're going to create similar things for Hamiltonian circuits. So first we're starting with the empty like set of edges, that we don't have any edges or vertices added to this array, or the things that we use for store the nodes for our path. So then we have 3 other, like in this case we have 3 nodes, because our start node is A. Okay, so we have B, C, and D. So that's when I is equal to 1. Then on the next level we have again B, C, and D, because if B is promising, so we are going to like do it for all other nodes of the graph, and exactly for the other ones. And finally, when we have, let's say, 2 nodes in the 2 nodes in our list plus the one that is A, finally we're gonna like visit the last node and going back to the start node that is A. So at first level we will have only 1 node. At next level we have n minus 1. On the third level we have n minus 1 to the power 2 and n minus 1 to the power 3. Okay, and so if we want to write all of these things together, the number of nodes that we have in this Hamiltonian circuit tree for this problem, it's gonna be that is equal to n minus 1 to the power n minus 1 divided by n minus 2. So that's the number of nodes in Hamiltonian circuits, and it's a state space tree. Next, I'm gonna show you the backtracking algorithm for solving the Hamiltonian circuits problem. That's the Hamiltonian algorithm, or using the backtracking approach. So similar to other backtracking algorithm, okay, we have a promising function, promising part, and also the main part of the algorithm. So if a node in the state space tree is promising, and so it checks that if we are already have visited all the nodes, so that's I is equal to n minus 1, because the first node and this start and n node both are same, so that's why we are comparing with n minus 1, that is the number of nodes minus 1. Then we are printing the v index, and v index is an array that contains the path or like the vertices that says that from each node we should go to the which other node. So for example, from A, on the example that we saw, from A we are going to B. So the first item will be A, the second one will be B. Otherwise, so if we are not done yet, so for every other vertex that we have in our graph, so we are putting, we are assuming that this is going to be a solution, so we are putting in that index, that vertex into the list of our indexes, and we are calling this Hamiltonian recursive function again with now with the new indexes. In the promising function, what we are doing is, first of all, we have to check that if I is equal to n minus 1, that means that if we the start node is equal to the last node, if this is the case, okay, so we have to check that the start and the last should be same. Okay, so start and last should be same. Otherwise, it's gonna say that the promising should be false. Otherwise, if n is not equal to n minus 1, it means that somehow we are in middle of our path to the destination, that is also the start node. Okay, if the nodes that we are comparing with at location I minus 1, okay, so if the node at location I minus 1 and in the current node that we are checking, if they are not neighbors, and that W is the adjacency matrix, or we can set the weight if they are weighted, okay. So if the weight is equal to 0, or they are not neighbors of each other, then also the promising is false. Otherwise, the promising is true means that so the nodes that we pick, they are neighbors of each other, so they are in the same path. So here, for example, you can see that let's say I is equal to 2, and so node can be let's say C. So index at location I minus 1 can be B, and because B and C in our example were neighbor of each other, so that's the promising is true. Then later we also need to check that for every other node that we had before, so checking that if we already had included that that vertex in our solution, also it's puts our problem, our solution to be false, is not promising. So because we wanted to make sure that we are visiting every node only once, so that's that part that we are checking, that we are not visiting any node more than once. And this is for all the nodes that we have visited so far. So that's J is for index of all nodes that we have already visited. So if we are I is equal to 2 and J is started at 1, so it means that we need to check that if the previous node is the same node that we are visiting now or not. If the question is if the answer is yes, so it means that we already visited that node, so we are setting is promising to false. That means that we violate the condition for Hamiltonian circuit. That means that every node should be visited only once. Otherwise, is everything fine? So then we are returning true as is promising. And then again, as we said in the main function of the Hamiltonian recursive function that goes and creates traverse the space state tree. Okay, if it's promising, then we are going further like to find the final solution. So that's the Hamiltonian circuit algorithm.